Okay, so continuing on the topic with degree sequences for a few minutes, here are a couple of exercises, but we've added an extra condition here. So let's see if we can find simple graphs with the following degree sequences. Or if we can't, we'll prove that no such graph can exist. Remember that simple means no loops, no multi-edges. All right, so like in the previous example at the end of the last video, we had one where we needed to use a multi-edge, or we could have used a loop in order to get the degree sequence. Now we're saying that's not allowed. So pause the video and see if you can do these two examples. All right, try to find graphs or try to draw graphs that have these sequences. All right, I'm gonna assume that you've done that. So you've attempted to do it. Now, if you may have been successful or not. If you weren't successful, then you tried to prove that that graph couldn't exist. And we're going to go over both of these examples now. So the first thing you should do is check the sum. Check the degree sum to make sure that it's an even number. Because if it's odd, then it's right out. Right? This is fine because we've got 6 and then 8, so that's even. Fine. This one, we've got 10, 14, 20, that's even, so that's fine. So, okay, so neither of them are as simple as saying that the sum is odd and therefore it violates the handshake theorem. So let's just jump right in and see if we can do these. Scroll down here a bit. So let's start with A. How many vertices would this need to have? Well, we have 2, 3, 4, 5, 6 numbers in this sequence. So I'm going to draw 6 vertices. There we go. There's some 6 vertices. And now I'm just going to start attempting to make this work out. So I need to have 2 vertices with odd degree. Let's see. I'm going to take this one. Sorry, 2 vertices with degree 3 in particular. I'm going to take this one, and I'm going to connect it to 3 other vertices. It doesn't really matter which 3. I'm just going to pick 3. There we go. So now this one has a degree of 3. Well, that's good. Now let's make another one with a degree of 3. I'm going to pick this guy over here. So now I'll pick this, and I'm going to attach this to 3 other vertices. Let's just do that one, and I don't know, this one over here. All right. So now what I want is for all of my other vertices to have degree 2. Well, these have degree 2. That's a degree 2. That's got degree 2. That's fine. But these other 2 vertices don't have degree 2. They so far have degree 1. But I can fix that because I could put an edge connecting them. So I could just get in here and go like this. Oops. Whoa, my goodness. I think I just accidentally rotated and blew up that number. All right. Get out of here. If I haven't mentioned it already, I hate touchscreens so much. All right. Let's look now. That single edge that I've introduced connecting those has given me the degrees that I want. That was pretty easy. We were able to come up with a graph that had that degree sequence pretty quickly. So this one is graphic. Done. All right, so now let's look at B. Well, we got 5, 5, 4, 3, 2, 1. Let's attempt to make such a graph. Again, I'm going to do 6 vertices. 1, 2, 3, 4, 5, 6. There we go. And again, I'm going to start with the largest numbers. I need to have some vertices of degree 5. And remember, with a simple graph, the only way to do this is to connect vertices to other distinct vertices. So if I have 6 vertices and I want to have one with a degree 5, then I need to connect that vertex to every other vertex in the graph. That is the only way I can do this. There's no other way to get a vertex of degree 5 in a simple graph on 6 vertices. This is a pretty key point, actually. It also, you can also take out of this that there is a maximum degree for a simple graph on a finite number of vertices. That may be important to you at some point. So that one is locked in, right? Say that's going to be degree 5, and now I need to pick another one to be degree 5. It doesn't matter which one I pick because so far all of these of degree are of degree 1. There's basically symmetry among all 5 of these other vertices. I'm going to pick this one over here to be my degree 5. Okay, I'm going to make that locked in once I'm done. There we go. All right, so far it's degree 1. I've got to connect it to every single other vertex in order to make it degree 5. There we go. Okay, I see a problem. And that is that one of the numbers, one of the degrees we're supposed to have in our sequence is 1. But with these two vertices of degree 5, I have discovered that every other vertex would have to have degree at least 2, which makes this impossible. So I think the result here, and in fact, correctly, the result here is that this is not graphic, but we still need to write a proof. So we can use what we discovered here in our proof. We're basically going to argue that, well, here, let's go ahead and write this out. We're going to argue that if 2 of 6 vertices in a simple graph if 2 have degree 5, each is adjacent to every other vertex because there's only 6 vertices, right? So each of those vertices of degree 5 has to be adjacent to every other vertex. Thus, every other vertex has degree at least 2, making degree 1 impossible. This is essentially a proof sort of by contradiction, saying, that would contradict the assumption. We didn't really make this assumption. It's kind of implicit. If we had assumed that such a graph existed, which is basically what we were trying to do here, like we were trying to create that graph, then this result here contradicts our assumption that we're supposed to have a vertex of degree 1. And then we can say, therefore, no such graph exists. Yeah. All right. So you had some problems like this on your assessment, and also, oops. Sorry. Okay. You have some problems like this on your assessment and also in the homework. And so I hope that these examples kind of help you to see what types of arguments you can make and what kinds of things you can do to figure out whether or not certain degree sequences are graphic or not. All right.